Welcome to Introduction to Space Engineering. In this series, we pull back the curtain on how humanity extends its reach beyond Earth. Before we look at the complex machines, we must understand the core ideas: how space science and space engineering work together, the challenging space environment that shapes every design, and the strict mission blueprint that guides us from an idea to a working mission in space. Let's first be clear about the roles. Space science is about asking the big questions like, how did the universe begin? Is there life beyond Earth? How do stars and galaxies change over time? Scientists observe, form theories, and study data to build our fundamental understanding of the universe. This is about discovery and seeking knowledge. Space engineering is about applying this knowledge to solve problems. Space engineering asks, how can we build a spacecraft to study other planets in our own solar system? How do we keep people alive for months and years in space? How do we land a complex rover safely on Mars? Engineers design, build, test, and operate the systems that allow for scientific research and human spaceflight. If science gives us the questions about the universe, engineering creates the tools to answer them. They work together. New scientific questions drive engineers to create better technology, and new engineering tools allow scientists to explore even more. Every piece of equipment sent into space must deal with an extremely harsh environment. These are the main challenges that affect nearly every engineering choice. First, the vacuum of space. This has several important effects. Materials can outgas, which can contaminate sensitive optical tools or thermal control surfaces. Also, heat transfer changes significantly because without air, convection becomes challenging and radiation and conduction become important ways the heat moves in space, completely changing how we manage temperature. And these are just the tip of the iceberg. Next, and very important, is space radiation. Beyond Earth's protective atmospheric and magnetic fields, spacecrafts are constantly hit by high energy particles. We mainly have to worry about two types: galactic cosmic rays, or GCRs, which are high energy particles from outside our solar system, creating a steady background radiation, and solar particle events, or SPEs, which are strong, sudden bursts of particles released during solar flares or eruptions from the sun. These particles can cause electronic problems like single event upsets, single event latch ups, and gradually total ionizing dose damage, which can lead to temporary or sometimes permanent part failure. For human missions, shielding against radiation becomes even more important because space radiation greatly increases the risk of cancer and other illnesses. Engineers use tough, radiation-hardened electronics, carefully place parts, and use multiple layers of shielding materials. Mission planners also choose orbits in a way that reduces exposure, for example, by avoiding long periods of time staying within the Van Allen belts. Then, consider thermal extremes. The surfaces facing the sun can reach hundreds of degrees of Celsius. At the same time, shaded surfaces can drop to hundreds of degrees below freezing in minutes. This fast heating and cooling creates strong physical stress on materials and structures, which can lead to cracks over the mission's lifetime. To keep sensitive parts within their small working temperature ranges, engineers use advanced thermal control systems, which we are going to call TCS from now on. Passive TCS elements include special coatings that control how much heat is absorbed or released, and the very common multi-layer insulation MLI, those crinkly gold blankets that you've seen on spacecrafts. Active TCS involves internal heaters, fluid loops, adjustable vents or louvers, and cryocoolers for precise temperature control of specific instruments. The TCS is a constant battle to balance internally generated heat with heat absorbed from the sun and the heat radiated into space. Microgravity, or feeling weightless that we think of, always creates unique design challenges. Liquids behave very differently without gravity. They do not settle, making fuel management in tanks complex. This needs special capillary or bladder systems. For human systems, managing waste and ensuring enough water intake becomes tricky. Structural parts, while not needing to hold their own weight in orbit, must be designed to handle vibrations and sudden forces, especially during launch and orbit changes, where the lack of gravity changes how they behave. Finally, the increasing danger of orbital debris. This collection of non-working human-made objects, from old satellites, old rocket parts to tiny even paint flakes, pose a serious collision risk. Because of their extremely high velocities in orbit, about 7 to 8 kilometers per second in low Earth orbit, even a very small piece can hit a spacecraft with enough energy to cause great damage. Engineers use strategies like Whipple shields or other protective layers. They also design for demise architectures where materials safely burn up when re-entering the atmosphere. More and more plans for active debris removal are being made to reduce the amount of dangerous objects in space. Because of these extreme conditions, space missions cannot be planned without a careful process. They follow a highly structured, step-by-step plan called the mission life cycle, which can be divided into several distinct phases. This careful approach helps manage complexity, reduces risk, and ensures that every step can be tracked from the first idea to the mission's completion. It starts with phase A, which is the concept and feasibility studies phase. Here, the broad goals of the mission are set. Scientists and engineers brainstorm ideas, do early studies, and identify possible technologies. The main goal here is to find out if a mission can even be done, both technically and financially. Next is phase B, preliminary design and technology development. In this phase, the main design of the system is created. Major parts are identified, early requirements are written down, and important technologies that need more development are found. This phase involves many trade studies, iterations where different design choices, for example, among the different kinds of onboard propulsion systems to be used, are carefully compared based on cost, weight, power, and performance to find the best solutions. Phase C, detailed design and fabrication. Every single part is specified, detailed drawings are made and built. Here, engineers select the exact components, define how different parts connect, and build the various parts of the complex spacecraft. Phase D is the assembly, integration, and test phase. This is often one of the most important phases and sometimes one of the most longest ones. It involves physically connecting and rigorously checking every component, every part, and finally the complete spacecraft as a whole. This includes extensive environmental testing, exposing the spacecraft to simulated launch vibrations on large shake tables, acoustic testing in special sound chambers, and long thermal vacuum testing in huge chambers that copy the vacuum and extreme temperatures of space. Electromagnetic compatibility testing makes sure different parts of the spacecraft do not interfere with each other. Beyond these environmental tests, extensive functional testing is also performed. This involves powering up the spacecraft, running through all its operational modes, sending and receiving simulated commands, and verifying that all instruments and systems perform their intended functions exactly as designed. Every single line of code is tested and every response is logged and analyzed. This rigorous testing phase is expensive and time consuming, but it is absolutely essential to minimize the risk of failure once the spacecraft is launched and it becomes unfixable. After surviving AIT and its journey to the launch pad, the spacecraft finally takes flight. This marks the beginning of phase E, or mission operations, the phase where the mission comes to life. Launch operations involve the final countdown, propellant loading, and the intense moments from engine ignition to orbital insertion. This critical period is managed by a dedicated launch team working closely with the rocket provider. Once the spacecraft is safely separated from the launch vehicle in its preliminary orbit, the real work of in-orbit operations begins. Ground stations are geographically distributed antenna dishes that communicate directly with the spacecraft, sending commands, which is uplink, and receiving data, which is downlink. These stations connect to a central mission control center staffed by a team of highly specialized engineers and operators. These include flight controllers who monitor the spacecraft's health and status using real-time telemetry data. Flight dynamics engineers track the spacecraft's precise orbit, predict its path, and plan necessary orbital maneuvers. Payload operations teams manage the scientific instruments. Anomaly response teams are constantly ready to diagnose and troubleshoot unexpected issues on the spacecraft. Throughout the mission, massive amounts of data are collected, processed, archived, and then distributed to scientists and users worldwide. Mission operations can span years, even decades usually. Finally, phase F, decommissioning and disposal. This phase deals with how to responsibly end the spacecraft's life, whether it's by guiding it to burn up in the atmosphere, moving it to a graveyard orbit, which is far away from our Earth, or for probes going to other planets, simply letting it drift into deep space. This step is becoming more and more important for reducing space debris. From the grand scientific questions that start our curiosity to the tiny failures caused by radiation, every part of space exploration demands a deep understanding of the environment and a disciplined engineering approach. The mission life cycle shows the careful planning needed to extend humanity's reach beyond Earth. In our next video, we will look at the basic physics that guides all space travel, which is orbital mechanics. We will talk about Kepler's laws, describe different types of orbits, and explore the invisible paths spacecrafts follow as they move through space. Till then, please subscribe to this channel and share this video with more space enthusiasts. And do not forget to check the links in the comments.